Hey folks, my name is Will Jessup, and this video is for software engineers who are in the process of learning how transformers work. So transformers are that thing that power large language models and ChatGPT, and there's already a bunch of introductory content about how they work, so that's not the purpose of my video. But if you've been going through this content, which I'll have in the description, and learning how they work, you're going to probably come across a couple of these code bases, like PicoGPT and NanoGPT. But when I went through this code myself and I was trying to learn from it, I felt that it complected either learning Python or frameworks with just what the transformer is doing, which is actually relatively simple mathematical operations. So let me show you what that actually means. Let's take a look at the model from NanoGPT. Okay, so here's layer norm. And what does it do? It calls f.layerNorm. So this doesn't teach you what layer norm does at all. You'd have to go and look into torch.nn functional to find out what this actually did. Another thing that this does here. So in self.transformer_h, we're iterating over blocks and calling block. And you might want to know, like, okay, what is it doing? So let's find self.transformer_h. Okay, so self.transformer and then module dict, like whatever this is doing, makes h, which is a module list, some list comprehension that makes blocks. Okay, let's look at what a block does. And so a block has some initialization, it extends another class, and it has a forward call. But wait a second, forward was never called anywhere. So, like, I guess if you know Torch, this isn't a problem. But I don't think we need all this wrapping for the educational purpose. Let's just keep it really simple. Let's look at, I guess, another example. So this is from PicoGPT. This is by far my favorite simple sort of educational bit of software. And it comes along with this blog post. So if you do want to learn about transformers, or if you haven't read this yet, do it. I'm really, really thankful to Jay for putting this together. But back into this code and why I think it could be simplified even further. So let's see. You've got lines like this. Now, if you've never done Python before, and I hadn't before a few months ago, this is like really complex. There's a lot of stuff going on here. The shape of K, Q, V heads is 4-dimensional, but Q, K, and V are 2-dimensional. And you wonder, like, why did that happen? Anyway, we just don't need this extra complexity. Another challenge is in this code is sort of tracking through parameters. So let's say I'm in multi-head attention and I want to know what C attention is. So let's find out where we got that. So we got it from MHA. It was passed in with this double splat thingy from attention, which was passed into attention into the transformer block. So transformer block got attention, expanded out from block. Block came from an iterator block in blocks. Okay, you see the point. If I just want to find out what a simple piece of data is, I'm going down the rabbit hole. And I find that to be unnecessary. Okay, so we're going to make like the simplest baseline sort of code library that does inference. So you run it and you can see it generate token by token. And again, use that as the baseline for sort of intermediate level stuff. I've also built some little explorer tools. This is a weights and biases explorer. So this visually shows you the relative size of each of the weights in the model. You can inspect it, sort of zoom in on individual blocks and stuff. And then I've made some diagrams. And anyway, we're going to be sort of checking out this stuff throughout the video. And this will be in the description for you to check out at the end. Okay, so I recorded the actual refactoring of the code the other day. So let's just jump over to that. As a starting place, I guess, let's just run this and see how it works. And this will be the basis for the changes that I want to start before we get into the key value cache. So you see, you type in the name of the file, and then not all heroes were capes, and this is what we want to complete against. And it says, comma, but they are all heroes. So before we make any changes, let's just copy this over into a new file. I'm calling it SimpleGPT2. And we're going to start making the changes from here. Let's just change over file name. Capes. Okay, I want it to generate tokens one at a time so that I can actually see what's being generated. Another change that we'll just do right up front is I don't want to pass in as sort of a non keyword argument parameter what this prompt is. The reason why is we're going to add batching in next to see how that actually works. And we're not going to be passing those in as parameters. Okay, so first thing, let's do the prompt. So we're just passing in the prompt into here. The second thing is to see these tokens be streamed out one at a time. So where we get the tokens out is at the end of the generate function. Out of GPT-2, we're getting logits. Then we take the last index of the logic, get the largest one, argmax is the largest one, and that's our next ID. So we can just print the next ID here. Actually, I have to decode it. So we're going to use the encoder, decode, and it's going to take an array. Okay. Okay. The problem is the encoder isn't actually available to us because we've only imported it here within this main function. So let's move that up to the top. Move some of these sort of parameters that it needs up to the top too. I don't need to be calling these in as arguments. So like, we'll just not do it. Okay, cool. Now, when we decode each of these, I don't want them to be an individual line. I want them to sort of be on the same line. So we're going to like do flush is true, and that will do it. So let's see how this works now. And you see we still have this like progress bar. I think that we need that. Let's remove the progress bar. Try again. There we go. Awesome. Okay, so this is what I want. I want it to stream the outputs all at the same time. Next thing about sort of simplifying is you'll see I call the main function, and the main calls generate. Generate is calling GPT-2, GPT-2. GPT-2 is calling transform block, transformer clock, so I'm calling multi-headed attention, and so on. And each of these is passing in all these variables. But because when we run through the transformer, and I've got a diagram here, you're like running through each of these linearly, and I don't see a reason for separating them out into individual functions. I mean, I guess if you're going to be doing state-based sort of work within here, which we'll be doing in the future, but for now, we don't need it. And what I want to do is just like see a simple flow through the whole thing. So I'm calling it SimpleGPT2. So let's just start like unraveling these functions, and we're going to do it really quickly. So the first one is going to unravel generate. So let's comment out generate, and let's take the code from generate, put it here. These. Okay. Now, in order for this to work, we need to name the things the same name. So let's just call these inputs. Now they're the same, and heads is your hyperparameters for the number of heads. And after each sort of like function that I'm moving in, we're just going to test that it works. Okay, cool. So we can get rid of that. The next thing is moving in GPT-2. We can delete generate. So GPT-2 does this code. Okay. It's equals your layer normalization. Okay, cool. Now into GPT-2, we're passing in this keyword arguments that's going to be expanded out. So what that means is we can just take params and put it here outside of these things. And I like this. It actually gives us more clarity for like where WTE came from and where WP actually came from. I don't have to track that it came from params. Like if I'm looking within the GPT-2 function, I'm going to say, what is WPE? And I have to go and look for it. So it doesn't help the readability, actually. Okay, so for block and blocks and block. And LNF comes from params. number of heads was passed in as, that's right, a keyword argument, which we can get here. VP is from params. Okay, now this work. Perfect. What's next? Now the transform block. Okay, so kind of same process. Comment that out. Paste it in. We don't need to return the X anymore because it's already here in line. And we're passing in block. So param blocks got block, and that is just going to be the block. ln1 block tension. We can see that the number of heads is kind of like it was passed through 3 functions so far where it's actually needed. 2, and guess what? Block MLP. Okay, see if this works. All right, making progress super fast. Next, multi-headed attention. Okay, so multi-headed attention like doesn't even have its own line. It's part of the residual stream. I'm going to explain this again in the Figma thing. So for each block in your transformer, you're doing this residual stream twice. So once after the multi-headed attention, and then once after the feed forward. And typically, like even in the papers, there's sort of 2 steps: layer norm, then multi-headed attention, layer norm, then feed forward. So I want to match that same style, just again for readability. So let's pull in the code, and then we'll see what we want to change. Sorry. So let's take the layer norm like outside of this, because this was done as the first parameter to multi-headed attention. So let's call it ln1 is the layer norm. Okay. So now so first we have layer norm, and then layer norm is what goes, so what goes into multi-headed attention. You can see that was X, and then X goes into linear. So now instead the layer norm is what goes into the linear. And I like this because it gives us a branching, like X is what goes off to the right on the side of this diagram. And we need a different variable here as the output of the layer norm, which goes into the multi-headed attention, which then gets mixed. So it just helps really with clarity, I think. So attention C was passed in as attention. Okay, so I think what we're going to do is get this is now going to be the output of your linear. Let's call this UKV. Okay, just so we have a different variable, because we're going to match it back down with X here in the end. We'll call this attention just for now. Follow me here. Okay. All right. So like we're really clear. This is your residual stream merging, and that this is chin. This is okay. Let's follow the same style, I guess. Now, okay, the number of heads. Man, this has been passed down 4 times now. I should know where it is. I wonder if I deleted it. Yeah, anyway, so I remember it was H grams. What else do we need here? C projection. C projection came from block, the attention block. Let's see if this works. There we go. All right. A little bit more readable every step of the way. So for your second layer norm, let's break it out again. So it's going to be 2 ln2. And that goes into the feed forward. Or called the MLP. I mean, it literally has the weights are called the MLP, but the function is called feed forward. A little bit confusing, but we can get there. I'm gonna keep the feed forward as its own thing. So this is gonna be feed out. This is your second residual stream addition. Okay, cool. Let's make sure it works. All right, so it's working. And what I like about this, I guess where we're at right now, is you can see there's a single main function that's called, and it does all the things that we want in a single pass with the iteration in line. And like, I like seeing that, you know, param blocks can be iterated upon for each block. Like, it's so much more clear for me just to work it through like that. Immediately, one thing stands out that we can change, and that's in the causal mask. So pause here for a second if you want to figure it out. All right, let's go. So the causal mask is based on the shape of X and nothing else. When you look at why it's here, I think it makes sense to be here due to, I guess, the diagrams for how this stuff works. Oops, you need a better one. So within multi-headed attention, you have the scaled dot product attention, and it has your query heads and your key heads, matrix multiplied, scaled, and masked. And so like, this is where people introduce the idea of masking. Kind of everyone does this. So here's another tutorial on blowing up the transformer architecture. And again,
bigger self-attention. And now value,
I don't know the exact point in here.
Self-attention.
He's doing this, but he's introducing the mask sort of right at the point that it's needed. Good for learning, not good for actually understanding like why is it introduced there. So let's move it out, because we can actually move the mask up to the first time that we generate X, because it's based on the shape of X. So already we're generating the mask like 11 less times. And when we introduce the key value cache, we only need the mask once. You only need it on the first pass when you actually generate the key value cache. You never need it again in inference. It's like, okay, that was really surprising. And you're going to see why when we get there. Another thing that I think could simplify from this code is this line. So in here, we are splitting what is the output of the linear projection. And let's actually talk about shapes. So your input shape, ln1, I think this is going to be the sequence length by the embedding size. So in this case, it's actually 768. And it's 6 because we have 6 tokens going in. So your length of your inputs is 6. When you do this linear, when linear is a matrix multiplication against your attention block C attention, this is actually getting expanded into 3 times 768. And that's because KQV has basically packed together in one matrix all that you need for each attention head, for your query, your key, and your value. I think that let's actually look at what this means. I've got sort of a visualization here that I built that helps. So in each individual block, we can go in and see, okay, we were in the attention. Yeah, that's right. So in the C attention, you've got 768 by 2304 is the size. Now, like, the sizes matter, and I think we should be tracking the sizes throughout this. I know that JMoody does it in this version. Yeah, and that's cool. Okay, so let's kind of keep at that and do it just where is needed with a real example, like what the numbers actually mean, because I think if you're not familiar with this and you're seeing, this is like sort of an abstract representation for someone that understands it. For me, learning from concrete examples, I think, is much more helpful. So the output of this is actually 6 by 2304. And then you split it twice. So like we're splitting it, and then we're taking the three things that it was split as and passing each of those into a lambda that then splits it again and then maps it into a list. Okay. You know what? The output of this is actually 3 times the number of heads, so 12. So it's splitting it 36 times. Let's just do that, like, and see what happens. Okay, so let's take the split, and we're going to do 3 times the number of heads. Let's see if that works. Oops, too many values to unpack. Oh yeah, because now we don't need to unpack it. But we're going to need to change this line because this expected a list of lists. Oh, let's go back to this. Okay. So what this output is in J's code is actually a list, 3 long, that then has your sequence size by the attention head size. Well, let's see. So it was 3 by something. 12, that's right. So it's like this, 3 by 12, 12 attention heads. Okay, so it's 3, meaning 1 for the query, 1 for the key, 1 for the value. Within each of those, it has 12 attention heads. Within each of the 12 attention heads, each attention head is the sequence length by the attention head size length. This is important to understand, and I don't think it was so clear in the tutorial. The thing that drives this number, 768, which is like your embedding size, and your embedding size is baked into your WPE and your WTE. You can see that here. So like your word token embeddings is 50,000, which is the vocabulary size times 768. So it's like baked in as the length there in this really small thing over here. Your word position embeddings, which is 1,024. So we have 1,024 possible position choices times your embedding dimension. So it's like baked in there, and it actually comes from this multiplication of 12 times 64. That's what drives the 768. So the 768 is like a derived number. It's not a foundational number of the model. Okay, but back to this line. So this thing is giving the shape of output, except it's not exactly the shape because a list is not, won't give us a shape. Let's see. So if we do QKV heads shape, this is going to blow up. Yeah, list object has no shape. And if you add it in MP, okay, thing. I think I screwed that up. I didn't press that. All right, cool. Whoopsie. So you see the shape. Oh, actually, that's cool. So you see the shape was 6 over 12 heads. And then in the next generation, it's 7, and then 8, and then 9. Okay, that's nice. But I think that we can pack these again in a simpler way. So that's what I'm hoping. I'm hoping you'll see why. So let's remove all that back to where we were, and then think about now what this line does. So what do we actually need to do? Now we need to take this K, Q, and V is actually, the Q is actually the 12th index of this model. Okay, so now if we just split it 36 times across, we need to grab the 0th index, the 12th index, and the 24th index, and then the 13th, then the 1st, 13th, 25th, etc., and pass those into attention. So that's what we need to do to change this line, to get this to work. So let's think about how to do that. We're not going to use zip anymore. what we're going to do is iterate over the number of heads. So for each head, or like be in heads, you're going to pass into attention. So let's do attention. But we're going to store the outputs in an array. And then we're going to do ID, oops, ID, and then arrows, oops again, plus the number of heads. ID. All right, so what this should do, let's do, and Q, K, and V is not, oh, that's right. So we no longer have Q, K, and V, we just have the attention heads. So we're just grabbing the different indexes of the attention heads that we need at the place that we need them. And this is, I mean, for me, this is really clear that everything is packed within this in a certain way. So let's attention. Let's append the output of this, but save it as a different thing first. In case we need to inspect it. Okay, now I wonder if this works. Right. So we're going to do a range 0 to 10 head. Oh, there we go. Okay, that worked. Maybe we want to do something like this. That could be fine. All right. I think at this point, we've really simplified this down. And we're ready to move on with the next step.